Imagine trying to power an entire suburban neighborhood using like a single electrical outlet in your kitchen.
Yeah, that's not going to end well.
No. I mean, if you actually tried to do that, the wires in your walls would literally just vaporize instantly.
Completely.
But believe it or not, that is exactly the kind of physics crisis that the world's biggest tech companies are facing today. So welcome to the Deep Dive.
Glad to be here.
It is Thursday, May 21, 2026. And today, we're tearing into a huge stack of breaking news alongside this incredibly detailed, brand new 2026 Tech Outlook report from CMB International.
It is a massive report, honestly.
Yeah, and our mission today is to figure out how the artificial intelligence arms race has just, well, how it's fundamentally mutated.
Mutated is definitely the right word for it.
Right, because for the last couple of years, it's been this really straightforward battle of, who has the fastest computer chip.
Just a component race, really.
Yeah, exactly.
Yeah.
But today, it is a total war of infrastructure. So let's unpack this. Because what is happening right now, these massive windowless data centers, is going to dictate everything from the future of the internet to why that smartphone sitting in your pocket right now might actually be getting worse.
Yeah, it's a massive systemic pivot. I mean, we are no longer looking at just a component level race at all. It is a full-blown system level war.
Right.
And when you look at the sheer physical scale of what is being built to support these AI models, it's genuinely staggering.
It's wild.
We are talking about re-engineering the very foundations of how electricity and data physically move.
And I don't think anything illustrates that better than the huge bombshell that dropped today in the news.
Oh, absolutely.
Yeah, AMD's CEO Lisa Su just announced a $10 billion investment in Taiwan's industrial ecosystem.
10 billion with a B.
10 billion. I mean, to put this into perspective for you, in the past, companies like AMD just focused on building a faster engine, right? The chip itself.
Exactly. They made the engine and let someone else build the car.
Right. But now it feels like they're having to redesign the entire car, the factory that builds the car, and like the actual roads the car drives on.
Yeah.
So why is AMD pouring $10 billion not just into their own chip manufacturing, but into this massive, sprawling network of third-party mechanics and packaging companies?
Well, if we connect this to the bigger picture, this is really about Taiwan upgrading its entire role on the global stage.
Okay, how so?
It's shedding that old identity of just being, a manufacturing base. It's transforming into the indispensable core hub of global AI infrastructure.
Right, the center of gravity is shifting.
Exactly. What Lisa Su announced isn't just about handing cash to a single foundry to stamp out more silicon. They confirmed today that their 6th-generation EPYC server processor...
Right, one code named Venice, right?
Right, Venice. It has officially entered mass production. And the critical detail here, the thing you have to understand, is that Venice is being built on TSMC's 2-nanometer process. Yeah, that makes it the industry's very first high-performance computing product to achieve mass production on a 2-nanometer node.
Which, I mean, that is an incredible technical milestone just on its own. You're talking about transistors that are, approaching the size of individual atoms?
Getting very close, yeah. It's mind-boggling.
But the announcement didn't stop at just the Venice chip, did it? They introduced this massive thing called the Helios rack scale platform.
Right, exactly. And Helios is where that system-level war we talked about really comes into focus.
Okay.
It integrates those 2-nanometer Venice CPUs with their new MI450X GPUs, and AMD is explicitly targeting multi-gigawatt data centers for the second half of 2026.
Multi-gigawatt, just insane power scale.
Completely. But here is the catch. To build a system of that magnitude, you can't just, hand a blueprint to a factory and ask them to assemble it.
Right, it's not IKEA furniture.
No, not at all. You need unprecedented collaboration across so many different disciplines. That is exactly why AMD is partnering so deeply with these Taiwanese giants like ASECCL and PowerTech, which is also known as PTI.
Okay, and what are they actually building together?
Together, they are scaling up a technology called 2.5D panel-level embedded bridge interconnect, or EFB for short.
Okay, wait, back up. Let's translate that for a second, because that is a very dense wall of jargon.
Fair enough, yeah.
What does 2.5D panel-level embedded bridge actually mean? Like, are we building chips upwards into 3D towers, or what is physically happening here?
It's a great question. So think of it kind of like city planning.
Okay.
In the past, if you wanted a more powerful chip, you just tried to build one massive, flawless piece of silicon, like one giant, sprawling mega building.
Right.
But as chips get bigger and bigger, the chances of a microscopic defect ruining the whole thing just skyrocket it.
Which makes them incredibly expensive to produce.
Exactly. So the industry shifted to what we call chiplets. You build smaller, highly specialized neighborhoods of silicon, and then you connect them.
Ah, okay. So the bridge in Embedded Bridge is literally the highway connecting those little neighborhoods.
Precisely. The embedded bridge is this tiny, high-density piece of silicon that is literally embedded in the packaging layer below the chips. It acts as a superhighway between them.
Got it. And the 2.5D part.
That just means they sit side by side on top of this connective layer. They aren't fully stacked on top of each other like a true 3D skyscraper.
Okay, that makes perfect sense.
But the real breakthrough in AMD's announcement today is the panel level part.
Right. What does that change?
Historically, all this advanced packaging was done on round silicon wafers, which is very expensive, and it really limits how much you can produce at once.
Because you're wasting the edges of the circle.
Exactly. Panel level means they are moving this whole packaging process onto much larger rectangular substrates.
Wow.
It focuses heavily on scalability and cost efficiency. It allows them to connect these chips with massive bandwidth, but in a way that can actually be deployed economically at a truly global scale.
That makes a lot of sense. So they're essentially figuring out how to mass produce the highways, not just the individual buildings.
Yes, perfectly said.
And, Lisa Su's own words really hammer that home. Today she said, quote, "Our products could not have grown and succeeded without the entire Taiwan ecosystem walking alongside us."
Yeah, that's a very telling quote.
It is. She explicitly noted that they are, quote, "ramping capacity like crazy."
And that capacity is fiercely complex to build. I mean, it requires specialized mechanical parts, advanced substrates, and these insanely complex liquid cooling manifolds.
Right.
It requires dozens of highly specialized companies moving in perfect lockstep.
Which is a perfect pivot, logically, to the next major theme in this CMB International report.
Oh, the ASICs.
Exactly. Because AMD is doing all of this to build the ultimate off-the-rack supercomputer for the open market, right? And NVIDIA is doing the exact same thing.
Right.
But there is this massive plot twist happening behind the scenes. So Google, Meta, Amazon, the actual hyperscalers who are buying all these chips, they are realizing that buying off-the-rack suits doesn't really work when you are a giant.
No, they want to make their own clothes.
Exactly. We are seeing the silent rise of custom ASICs.
Yes, application-specific integrated circuits.
Right.
So an ASIC is a chip designed from the ground up for a highly specific task. In this case, running proprietary AI algorithms. It's not for general-purpose computing at all.
It only does one thing, but it does it incredibly well.
Exactly. The major cloud service providers, the CSPs, they're aggressively accelerating their in-house ASIC adoption because they desperately want autonomy and efficiency.
We want to control their own destiny.
They do. They are tired of being entirely dependent on the pricing power of NVIDIA or AMD. And they know that silicon perfectly tuned to their own software is always going to run faster and cheaper than a general-purpose chip.
Oh, okay. But I kind of have to push back here.
Sure.
Because right now, NVIDIA seems completely untouchable. I mean, they are the trillion-dollar gorilla in the room. Is anyone actually buying enough of these custom chips to make a real dent in the market? Or is this just like Google doing a fun science project?
Oh, no, it is a very real threat.
Really?
Yeah, the numbers in the CME report are striking. They forecast that global AI training server shipments are going to jump 50% year over year. That brings us to 2.32 million units in 2026.
That is massive growth.
It is. But within that expanding pie, the market share for ASIC AI servers is projected to jump from 21% in 2025 to 25% in 2026.
Wait, 25%. So 1 in 4 of these new AI servers will be running on custom silicon.
Yes, completely bypassing the traditional GPU giants.
1 in 4. Okay, that is not a science project. That is a revolution. Who is actually driving that kind of volume?
It is a who's who of tech royalty, honestly.
Yeah.
In 2026, we are seeing the aggressive ramp-up of Google's TPU v7, AWS's Trainium 3, Meta's MTIA 3, and perhaps most intriguingly, OpenAI's upcoming debut, ASIC.
Oh, wow. OpenAI is making their own, too.
Yep. But what's really fascinating here is the ripple effect this has on the physical supply chain.
Right, because if Google designs a custom brain in the lab, They still need someone to build the actual physical server box that the brain goes into.
Right.
Google isn't operating metal stamping presses,
Precisely. These custom chips require highly customized server designs. The power delivery, the physical layout, the cooling, it all has to be built from scratch to match that specific ASIC perfectly.
Okay.
And this is creating incredibly lucrative, wildly complex work for system ODMs.
The original design manufacturers.
Yes. Companies like Quanta, Inventec, and Wiwynn.
So just to explain an ODM for you, they aren't designing the chip, and they aren't writing the AI software. They are basically the master mechanics.
Yeah, that's a good way to look at it.
They are the ones figuring out how to actually bolt this experimental engine into the chassis without the whole thing just catching fire.
That is a perfect analogy. Historically, these ODMs just assembled standard off-the-shelf parts, but now they are transitioning into deep integrated mechanical, electrical, and thermal engineering right alongside the cloud giants.
And that brings us exactly to the physical reality of what we are talking about today.
The heat.
The heat. Because whether you are using an off-the-rack AMD Helio system, or a giant NVIDIA rig, or a hyper-custom Google TPU V7, you still run headfirst into the exact same brick wall.
Thermodynamics.
Yes. We are putting the power of a small neighborhood into the space of a refrigerator. How is this stuff not just melting into a puddle of expensive slag?
It is genuinely one of the most difficult engineering challenges of our time. I mean, the power and thermal management requirements are undergoing a complete paradigm shift.
Right.
Traditional air cooling, just blowing cold air over hot metal with loud fans, is officially dying. It simply cannot keep up with the physics anymore.
It's just not enough.
No. The CMB report notes that liquid cooling penetration in global AI training servers is surging to 40% in 2026.
Wait, 40%?
Yep.
That implies the other 60% is either legacy hardware or they are just pushing fans and air cooling to their absolute theoretical limits.
Pretty much.
Give us a sense of the actual heat we are talking about here. Like, put numbers to it.
Okay, let's look at a single chip's thermal design power, or a TDP. We are now routinely exceeding 1,000 watts for a single piece of silicon.
Wow.
And NVIDIA's upcoming VR200 platform, the Vera Rubin architecture, that maxes out at a staggering 2.3 kilowatts per chip.
Over 2,000 watts. For one chip.
Yes.
That is like having a high-end commercial space heater concentrated onto a surface the size of a drink coaster.
Exactly.
Yeah.
Picture putting 144 of those chips into a single VR200 NVL144 rack.
Oh my.
That single rack, which is roughly the size of a large vending machine, will consume 240 to 260 kilowatts of power.
Okay, my mind is struggling to process that. Let's do the math here. An average house uses, what, maybe 1 or 2 kilowatts at any given moment, unless the AC is blasting.
Somewhere on there, yeah.
You are telling me one server rack is using the power of over 100 homes.
Correct.
How do you even plug a 260 kilowatt rack into the wall?
Well, that is exactly the crisis. You can't.
Right.
It is forcing a complete redesign of the data center's electrical grid. Historically, servers ran on 48-volt or 54-volt architectures, but it all comes down to simple physics. Power equals current times voltage.
Okay.
At 260 kilowatts, if you keep the voltage low at 48 volts, the current has to be massively high to deliver that power.
Right.
And to carry that much current, your copper bus bars, the thick metal strips that actually deliver the electricity inside the rack, they would literally have to be the size of tree trunks.
They wouldn't even fit inside the cabinet.
Exactly. Plus, you lose a massive amount of energy as heat just trying to push that much current through the copper.
Because the copper itself acts as a resistor.
Exactly.
So the solution is to pump up the voltage.
Yes. High voltage DC, or HVDC. The industry is rapidly shifting to 400-volt and even 800-volt architectures right inside the rack.
Wow. 800 volts.
Yeah. By drastically cranking up the voltage, you can lower the current. That means you can use significantly less copper, save physical space, and drastically reduce the energy that gets lost as heat.
And I imagine the power supplies have to change too.
Oh, completely. To support this, the power supply units are evolving quickly. Their density is doubling, with individual units now pushing 12 kilowatts or more.
Okay, so you've solved getting the massive power to the chip efficiently. But you still have a chip generating 2.3 kilowatts of raw heat.
Yeah.
You mentioned liquid cooling earlier, but how does liquid cooling actually evolve to handle something that hot?
This is where the mechanical engineering gets truly beautiful, honestly. Right now, liquid cooling usually involves a cold plate. It's a metal block with liquid flowing through it, and it just sits on top of the chip.
Right, pretty standard.
But there is always a tiny microscopic layer of thermal paste between the bare chip and that metal plate. It's there to fill in the microscopic air gaps.
Okay.
And that paste, no matter how good it is, acts as a thermal resistor. When you hit 3,000 watts, which we will see very soon, that little layer of thermal paste becomes a critical bottleneck.
The heat just physically cannot transfer through the paste fast enough, and the chip just cooks itself.
Right, it can't escape. So the report previews a new technology called microchannel lids, or MCL.
Okay, how does that work?
We will see pilot runs in the second half of 2026 and mass production in 2027. Instead of bolting a separate cold plate onto the chip with thermal paste, they are literally machining microscopic cooling channels directly into the chip's silicon packaging itself.
No way.
Yes. The liquid will flow literally millimeters away from the active silicon, entirely bypassing that thermal resistance layer.
That is wild. We are plumbing microscopic water pipes directly into the brain of the computer.
Exactly.
But, here's the thing. Keeping these chips perfectly powered and perfectly cool is entirely useless if they can't actually talk to each other fast enough.
Very true.
Which brings us to the data bottleneck.
Yes, the interconnects. If the chips are the brains, interconnects are the nervous system of the AI data center. And the speeds required right now are literally breaking traditional wiring.
I noticed this in the CMB report, and I actually need you to clarify this for me.
Sure.
The report says the VR200 is shifting back to, quote, mid-plane PCB designs. What does that mean physically? Like, are we building highways straight through the middle of the server?
Essentially, yes. So a PCB is a printed circuit board, the green board you see in most electronics.
Right.
Previously, to get data signals from one side of a server rack to another, they used a lot of overpass cables flying right over the top of the components.
Just a tangle of wire.
Exactly. But at these new massive bandwidths, those cables create too much physical clutter and they block the airflow.
Oh, which ruins the cooling.
Right. So a mid-plane PCB design embeds a massively thick, highly complex circuit board vertically right in the dead center of the chassis. It acts as a central spine.
Okay.
Components plug directly into both sides of it, meaning the data travels a much shorter distance through a solid board rather than having to travel through a messy spider web of cables.
Okay, that makes total sense for inside the box.
Mm.
But when you do need cables to connect different parts of the rack, the report talks about moving away from D to AECs.
Right. So DC stands for direct attached copper. It is just a standard passive copper cable. It's cheap, it's reliable.
But I'm guessing it has a speed limit.
Exactly. As data speeds increase, an electrical signal degrades much faster over copper. At the extreme bandwidths AI requires, the signal just dies and turns to pure noise after a meter or two.
Just fades away.
Yeah. So they're shifting to active electrical cables, or AECs.
And what exactly makes them active? Do they have their own power?
They do, and they literally embed tiny, intelligent silicon chips called retimers directly into the heads of the cable itself.
Oh, wow.
These retimers take the degrading electrical signal, clean it up, amplify it, and shoot it down the line. It allows for much longer cable runs within the rack without losing any data.
But, even an active copper cable has limits when you need to connect thousands of racks across a massive building, right?
Absolutely.
And this is where this report gets into pure science fiction for me. It talks about CPO, co-packaged optics, and OCS, optical circuit switches.
Oh, this is the absolute frontier of networking right now.
Break it down for us.
Traditionally, you send an electrical signal, a laser converts it to light, it travels down a fiber optic tube, hits a switch, gets converted back to electricity so it can be routed, and then converted back to light.
Which sounds like a lot of extra steps.
It is. That conversion takes precious nanoseconds and a lot of power.
Yeah.
OCS, an optical circuit switch, completely skips the conversion. It is essentially a switch that uses arrays of tiny microscopic physical mirrors. These mirrors physically tilt and pivot on a microscopic level to bounce the actual beam of light from one port to another.
Wait, hold on. Actual physical mirrors moving around to bounce lasers
Yeah.
inside the server.
Yes. It routes the data at the literal speed of light without ever having to convert the optical signal back into electricity.
That is incredible.
It offers ultra-low latency and massive energy savings just because you aren't doing that continuous electrical conversion over and over.
Okay, so let's step back for a second and look at this. We have microscopic water pipes etched directly into silicon. We have 800-volt power grids dodging copper tree trunks. And we have tiny mirrors bouncing lasers.
It is an absolute marvel of human engineering.
It really is.
Yeah.
But all of this extreme engineering comes at an extreme cost. Which brings us to the final piece of the puzzle. You, the listener.
The real-world impact.
Exactly. Because the CMB report highlights something called the memory supercycle. And we need to explain why this multi-billion-dollar AI infrastructure boom actually means that your next smartphone might cost more or, bizarrely, actually have worse specs.
It is a brilliant point in the report, and it really shows the unintended consequences of global resource allocation.
Yeah.
These massive AI servers we just discussed, they require an astronomical amount of high-bandwidth memory.
Right, to process all that data.
And because the cloud giants, Microsoft, Google, Amazon, because they are locked in this existential arms race, they are completely price insensitive.
Meaning they don't care what it costs.
Exactly. If the price of memory chips doubles overnight, Google doesn't care. They just pay it. The AI server ODMs simply pass that inflated cost directly through to the client.
Okay, so it's like trying to buy flour at your local grocery store. But a massive industrial bakery just moved to town.
That's a great way to look at it.
Right. They have unlimited money, and they're willing to pay triple the price for every single bag of flour on the shelf. And the local pizza shop just can't afford to bake anymore.
That is the exact dynamic playing out right now. Traditional memory like DRAM and NAND storage is a shared global resource.
There's only so much to go around.
Right. The massive demand from the AI data centers is constraining the supply across the board, and DRAM contract prices are surging as a result.
Okay, so apply your bakery analogy to a smartphone manufacturer.
Sure. So for a typical budget or mid-range phone, traditional memory makes up about 10 to 15% of the total bill of materials to build that device.
Which is a huge chunk of the cost when your margins are already tiny.
Exactly. Now, for a $1,000 high-end phone, memory is only 4 to 5% of the cost. So Apple or Samsung, they can absorb a price hike on their flagship devices.
They just eat the cost.
Right. But a budget smartphone maker, they absolutely cannot absorb a 50% hike in memory costs.
And they can't just raise the retail price of a $300 phone by $50 because their customers will just walk away. I mean, they are budget buyers for a reason.
Exactly. Furthermore, the CMB report notes that macroeconomic uncertainties and the fading of consumer subsidies in massive markets like China are putting even more downward pressure on these budget manufacturers.
So what do they actually do?
They are forced into what the industry quietly calls the despec trend.
Despec, meaning they actively lower the specifications of the new phones they are putting on the market.
Yes. To maintain their profit margins without raising the retail price, they might put 6 gigabytes of RAM in the new phone instead of 8.
Oh, wow.
Or they might use a slightly older, slower processor or downgrade the camera sensor. The AI boom is silently taxing the global memory supply, and the collateral damage is the performance of low to mid-range consumer electronics.
That is such a staggering, visceral connection.
Yeah.
When you buy a new budget phone next year and your Maps app lags or crashes because the phone doesn't have enough RAM, that frustration is the direct result of a liquid-cooled server farm in the desert buying up all the silicon.
It's all connected.
It really is. Okay, we have covered a tremendous amount of ground today.
We really have.
We started with Lisa Su dropping a $10 billion bombshell, committing AMD to a total system war, and transforming Taiwan's ecosystem to mass-produce 2-nanometer Venice chips and embedding them onto panel-level highways.
Yep.
We looked at the silent rise of custom ASICs, where Google and Meta are designing their own brains, forcing ODMs to become master mechanics.
Which is completely changing the hardware landscape.
Exactly. We explored the brutal wall of thermodynamics, 260-kilowatt racks, forcing a massive shift to 800-volt power grids, and microscopic liquid cooling channels bypassing thermal paste.
The microchannel lids, yeah.
We talked about AEC cables and microscopic mirrors routing data at the speed of light. And finally, we connected the dots to see how this insatiable hunger for memory is triggering a global squeeze, forcing smartphone makers to quietly downgrade your everyday gadgets.
It truly illustrates how deeply interconnected the modern tech landscape has become. I mean, a breakthrough in packaging substrates in Taiwan dictates the thermal dynamics of a massive data center in Iowa, which in turn directly impacts the price of a memory chip inside a smartphone being assembled in Vietnam.
It's incredible.
You just cannot separate the pieces anymore.
It is a totally global, synchronized machine. But before we sign off, I want to leave you with a final thought to mull over.
Yeah?
We have spent this entire deep dive talking about the center of the network, these multi-gigawatt, liquid-cooled, fortress-like data centers.
The massive infrastructure.
Right. But if you dig into a completely different section of this CMB report, It points out that all of this massive infrastructure is ultimately pointing toward a revolution on the very edge of the network.
The edge being the ultra-lightweight devices we actually interact with on a daily basis.
Exactly. The report predicts that AI glasses are about to enter what they call a smart glasses 2.0 era.
Oh, interesting.
Yeah, they are projecting shipments to surpass 10 million units in 2026. And they believe these glasses will eventually become the ultimate wearable, completely replacing our wireless earbuds.
That's a huge shift in consumer behavior.
It is. So I want you to imagine this. Somewhere out there today, a heavy-duty crane is lowering a 260 kilowatt server rack into a liquid-cooled data center.
Consuming insane amounts of power.
Right. It is consuming the electrical power of an entire neighborhood. And it is being built right now just so a lightweight, completely normal-looking pair of glasses resting on your face can understand and augment the physical world in real time tomorrow.
That is the true mind-bending scale of the transition we are living through.
It really puts it all into perspective. Thank you for joining us on this deep dive. And as always, keep questioning the infrastructure behind the magic of the tech in your life.